Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will continue talking about complex numbers. Let's see the first property. The second degree equation az squared plus bz plus c equal to 0, where a, b, and c are real numbers and a is never 0, has in C two distinct real roots, one double real root, or two distinct complex conjugate roots. Well, this looks like delta that you took in last year, and we have the same answers in the first two cases. In case delta is positive, we're going to have two distinct real roots, which are z1 is minus b minus radical delta over 2a, and z2 is minus b plus radical delta over 2a. And in case delta is 0, we're going to have one double real root, which is z1 equals z2 equals minus b over 2a. And the only difference happens here, in case delta is negative, in R we used to say that we have no real roots, whereas here in complex numbers we do have roots, and in fact we're going to have two complex roots which are conjugate to each other. They are minus b minus I, the square root of minus delta over 2a, and minus b plus I, the square root of minus delta over 2a. Notice here that we've used the square root of minus delta because delta in this case is negative, so if we multiply it by a minus it becomes positive, where delta, as you all know, is b squared minus 4ac. And remember, dear students, that all of these equations could be found using the calculator. So this is what we have to remember when the degree is 2. When delta is positive, this is what happens. When delta is 0, we have one double real root. And the only difference is that when delta is negative, we're going to have two distinct complex conjugate roots, which are given as follows. Let's see this example. We need to solve in C these equations. Let's begin with the first equation. It's an equation of degree 1. So we try to isolate z. We put z alone, non-z alone. Then if we take z in common, this is what we get. Then z would be minus 1 minus 3i over 1 minus 2i. And if we simplify it using the calculator, we get 1 minus I. This is the second equation. It's also of degree 1. So here we try to expand, then we isolate z, and this is what we get. Remember, always try to write the answer in algebraic form. Well, this is a second degree equation, so it will be solved using delta, or it could also be solved using the calculator. Delta in this case is 1. It's positive, so we get two real roots, which are negative 3 and negative 2. And in this case, this is also a second degree equation. So if we use delta, we get negative 31, which is negative. So the first root is minus b minus I, the square root of minus delta over 2a, and minus b plus I, the square root of minus delta over 2a, applying the last part of this procedure. Now let's see this application. You need to solve also and see each of the equations below. Try to solve it alone. Well, here if we expand, this is what we get. Remember, I squared is negative 1, so z squared and z squared will be eliminated, and z would be equal to 1. This is the second case. Try to solve it also. Well, this is a zero product equation, so each factor should be equal to 0. The first factor leads to z equals minus 1 plus I, and the second factor leads to z squared is negative 9, which is 9i squared. So z would be 3i or minus 3i. So we're going to have three roots, which are minus 1 plus I, 3i, and minus 3i. Well, try to solve this equation. Try to solve it alone. Now this is a second degree equation and delta is negative, so we apply the last part of this procedure. This is what we will have. Remember, the square root of 40 is 4 times 10, so this would be 2 the square root of 10, and if we simplify, this is what we get. This is the second root. Now try to solve this equation. Well, this is of degree 3, but if we just take z in common, we get a product such that one of the factors is of degree 1 and the other factor is of degree 2. The first factor leads to 0, and the second factor leads to one double root, which is z equals -3. Now let's see the second application. Z and z prime are two complex numbers such that there's a certain relation in between. This is the relation, and z is never minus I. The question is find z prime for z equals 1 minus I. So we just need to find z prime when z is 1 minus I. This is just a matter of calculation. Try to calculate it alone. So if we replace instead of each z 1 minus I, we get a 0. Now the second part asks to find z prime for z equals 2 plus I. We do it similarly. Try to do it alone. So in this case, if we replace each z by 2 plus I in the original relation, this is what we get. And after we multiply by the conjugate or we use the calculator, we get this answer. Now we need to find z when z prime is 2i. Pay attention. We need z when z prime is 2i. Also try to do it alone. So we replace z prime by 2i. This is what we get. If we cross multiply, we get such a quantity. If we isolate z, this is what we get. And dividing by I leads to this quantity, which is -1 minus I. Now find z for z prime is 1 plus I. Try also to do it alone. Well, if we replace z prime by 1 plus I, this is what we get. Cross multiplying leads to such a quantity, so z is -2i. Now the geometric representation of a complex number. In fact, a complex number could be represented algebraically in the form z equals a plus ib, and it could be also represented geometrically, and we will see how. The plane is referred to a direct orthonormal system. Z is a plus ib. A and b are real numbers, and M is a point whose coordinates are a, b. A is the real part of Z, and b is the imaginary part of Z. Well, MAB is called the image of the complex number Z, so M is the image of Z, and Z is called the affix of M. M is the image of Z, and Z is called the affix of M. The affix of point M is usually denoted by Zm in order to tell which point does it represent, so we usually write it as Zm. And we can, in fact, use different representations for M. We can state that M, we open parentheses, we write A plus IB, or we can write it using coordinates, or we just write M with affix Z, or we write Zm. All of these representations mean the same thing. We read M is a point with affix Z, or Zm is a complex number with image M. Now, in fact, these details are usually used at the beginning of each problem, so you have to get used to this language. Let's see. The plane is referred to a direct orthonormal system. Complete the table below. Well, this is the affix, and we need the image. If ZB is -2i, what do you think the image is? So, you know the affix and you need the image. In other words, you need to write the coordinates of the point. What would be the coordinates of point B in this case? I think this is very easy. It will be B, 0, -2. Well, here we have it in the reverse order. If we know the coordinates, what would be the affix? So ZD would be 1 plus 2i. And similarly here, G would be 3, 0. And ZL would be -1 plus 1i or -1 plus i. E in this case is 2, -1. F is 3i. And ZO is 0, 0. Now we have this grid. And we need to find the affix of each point of the points A, B, C, D, F, G, H, and O. In other words, you do know the coordinates of the points and you need their affixes. Try to do them alone and then compare your answers. Now let's see some of the properties. A, B, and C are 3 points with respective affixes ZA, ZB, and ZC. Z of vector AB would be ZB minus ZA, while I is the midpoint of AB if and only if ZI is ZA plus ZB over 2, and G is the center of gravity or centroid of triangle ABC if and only if Z of G is Z of A plus Z of B plus Z of C over 3. Now let's see this example. We have 3 points A, B, and C. This is ZA, ZB, and ZC. The first part asks to verify that BA is equal to BC as distances. My advice here is that you always draw a small figure or a sketch that represents the points. This is what I drew before. So I can see from here that BA is equal to BC. Let's try to prove it. Well, this is A, this is B, this is C. If we translate them into coordinates, this is AB vector, this is BC vector. So AB is the square root of 9 plus 1, which is the square root of 10. And BC is also the square root of 10. So we can tell that BA is equal to BC. Well, you could have calculated them using another way, which is AB is the square root of XB minus XA squared plus YB minus YA squared. You use the distance between 2 points. Now find the affix of point D, the fourth vertex of the parallelogram ABCD. Well, what do we mean by ABCD is a parallelogram? This means that the two vectors AB and DC are equal. Pay attention. Vector AB is equal to vector DC. So if we just apply Z's here, we can say that Z of vector AB equals Z of vector DC. So ZB minus ZA equals ZC minus ZD. We know ZA, ZB, and ZC, and this is an equation with one unknown, which is ZD. So we can tell that ZD is equal to 1. So D would be somewhere here. The third part, what is the nature of the quadrilateral ABCD? Justify your answer. Well, ABCD is a parallelogram having two equal consecutive sides, so it will be a rhombus. What is AB dot BC? This is AB, this is BC. It's equal to x prime plus y prime, which is 0. This means that AB and BC are perpendicular. So this is a rhombus with one right angle, so it will be a square. Now let's see this application. The first question asks to verify that AB is equal to CD and to show that the two lines AB and CD are non-parallel. Try to do it alone. Well, these are the coordinates of the points, and these are their representations. We need to prove that AB is equal to CD. We use the distance formula or the modulus of the vector. AB is radical 5, CD is also radical 5, so AB is equal to CD. Now, how do we prove that AB and CD are not parallel? This is AB, this is CD. We can see that x over x prime is not equal to y over y prime, so the two vectors are not collinear, which means that the two lines are not parallel. Now show that the two lines AD and BC are parallel. Try also to do it alone. Well, this is vector AD, this is vector BC. They are collinear vectors. In fact, BC equals double AD. So we can tell that AD and BC are parallel. The last part, what is the nature of the quadrilateral ABCD? Justify your answer. Try also to find the nature with justification. While AD is parallel to BC and AB is not parallel to CD, this means that ABCD is a trapezoid and it has two equal legs. So this is an isosceles trapezoid. Now Amir or Rima, solve in R this equation. Let's see what did they do. Amir wrote the equation. He factorized using difference of two squares. So the first one is 0 or the second one is 0. The first one gives a 3 or negative 3 and the second one has no solution because a square can never be negative. Well, Rima, she wrote also the equation. She factorized using difference of two squares. She said that the first factor is 0 or the second one is 0. For the first factor, she found 3 or minus 3, and for the second factor, she wrote that the squared is negative 9, which is 9i squared. So she found two roots, which are 3i or minus 3i.